Good morning, guys. Today we're going to look at combinations of functions. Pretty basic. Mostly this lecture is about notation with one new little addition that we're going to put in. So mostly it's just, again, about the notation. Combination, so if I do f plus g of x, all that's saying is f of x plus g of x. F minus g of x is f of x minus g of x. F times g of x is f of x times g of x. And f divided by g of x, or f over g of x, is where we just divide the functions. At this point right here, it really doesn't matter. I'll specify kind of what I'm looking for when we get to that. Sometimes I want you to just treat it like a rational expression where we're reduced, and then other times I want you to treat it like dividing a polynomial. Very important to keep in mind when we are dealing with fractions, we state restrictions always. And that kind of gets us into what the domain says here. This comment about domain of combined functions must meet the restrictions of the original functions and the final combined function. For example, if I was subtracting two functions and they had square roots in them, and the square roots happen to cancel out, the final function wouldn't have any domain restrictions because it wouldn't have any square roots left in it. But the original functions did have square roots in them. So that means that we have to use our square root domain restrictions. Remember, radicand has to be greater than or equal to 0. So those kind of things, when we're looking at the domain of the original, or domain of the final function, we want to look at all the domains from the two original functions and the domain from the final function, and put all that information in together to figure out what was the possible domain for the entire expression together. So that's it. Again, it's just a comment or a notation thing, and then we just either add, subtract, multiply, or divide, just going through doing the arithmetic. Composition functions are what we have next, so we'll put that stuff up here. It's a little bit different, but it's really like you've done before, just plugging stuff in, but instead of plugging a number, we're going to plug another expression in. So nothing major, if you'll just keep in mind what substituting and evaluating a function is. So give me a second, I'll get that information up for you. Next, we'll talk about composition functions. Notation-wise, this is f of g of x. This is not O, it's a little circle. So f of g of x, we think of that as f of g of x. So composition, and going back to function notation tells us that whatever's in parentheses, in this case the x, is what we're defining the variables. That's our input, that's our domain. That's what we're plugging into the equation. So when I have f of x equals negative x squared plus 2, f just tells me I have negative something squared plus 2, and then the x tells me what the something is. So f of anything is equal to negative of whatever that is plus 2. That's the way we've defined f in this particular equation, or this particular function. Well, f can be anything. I could say f of 1. Well, that tells me to plug in 1, right? I could say f of negative 3, and that tells me to plug in negative 3. You do your arithmetic. I could say f of t. That tells me plug in negative t. I could say f of smiley face, and that tells me to do smiley face. So negative smiley face squared plus 2. Whatever we're putting here, this is what we're defining. This is what's representing the domain. So it doesn't matter what we plug in. Well, what if I plugged in g? Well, that's pretty straightforward. It would be negative g squared plus 2. Well, what if instead of g, I did g of x? What would that be? Negative g of x squared plus 2. And that's what we're doing. We're doing a composition function. It just so happens we know what g of x equals. G of x in this case, f of g of x is equal to negative square root of x minus 1 quantity squared plus 2. So that's what a composition function is. We have an input function and then we have an output function. So the g function is getting input into the f function. So then you go through and do your arithmetic, and we can say that f of g of x, in this case, square root squared leaves us just the radicand. So we get negative x, distribute that negative, plus 1 plus 2, so it gives us negative x plus 3. Negative x plus 3. So that's what f of g of x in this particular, for this particular f and g would represent. So the internal function here is our input function, the other one is our output function. So the variable just gets dumped and replaced by not a number, not a variable, but an entire other equation or expression. Now how does domain fit into this? Well, if I looked at this right here, negative x plus 3, that's a polynomial because it's x to the first, so it has a whole number exponent. So we know whole number exponents have a domain of negative infinity to positive infinity. But the issue is this is not negative x plus 3. This is negative square root of x minus 1 squared plus 2 that created that. So when we're doing the domain of composed functions, it's got to meet the restrictions of the input function and the final function. So it's a little bit different than our combined functions where we added, subtract, multiply, and divide, where we look at both originals and the final. We're going to look at the input function, the function that's getting plugged into the other function, and our final combined function. So the final combined function, f, the domain of f of x, domain of f of x was negative infinity to positive infinity. Domain of g of x, square root, so remember, take your radicand, greater than, getting ahead of myself, greater than or equal to 0, so x is greater than or equal to 1. So that's the domain of g, so when we combine them together, we take this restriction and we get 1 to positive infinity for the domain of f of g of x. So the domain of f of g of x is the interval from 1 to positive infinity. So we would combine the two together. Most of the time, one of them is going to be negative infinity to positive infinity. It's just the way it happens a lot of time. Or they'll end up being the same. And then in which case you would just take the one that actually has restrictions on it. But if we'd had multiple restrictions, and we'll look at an example here in a little while that does, if we'd had multiple restrictions, we just kind of combine all that information into one master domain for this. So give me a second, I'll get some examples up here of actually figuring out what composite functions are, you know, creating some composite functions, and then evaluating using this idea of composite functions. Okay guys, right now I want you to pause the video and take a crack at these. See if you can evaluate g of f at -2 for these two functions, and evaluate f of g at -2 for those two functions. Then come back and do the composition for each of them. So go through, try to evaluate each of the compositions at -2 and try to create the compositions. This one will kind of see how you kind of put all this together and see if you can actually figure out how to evaluate using all these composition rules and things like that. So pause the video, I'll hang out right here, and we'll see what you got in a couple minutes. Okay, hopefully you were able to get these solutions. Let's check your work and see how you did. Now there's two ways I can go about it. First way, I can go through and I can do the composition first. If I want to evaluate, I can always just plug it in, okay? G of f means f is going to get inputted into g. So now f, so g is my output function, f is my input function. So we're going to take f, the f equation, and input it into the g equation. So as I go through, I like to write my g equation first, but I'm going to put parentheses where the x was. So it's no longer 1 over x minus 6, it's 1 over something minus 6, and that something is the f equation. So I take the entire f equation, x squared plus 2x plus 3, and we just go through and do the arithmetic. So 1 over x squared plus 2x, there's no like terms, so it stays x squared plus 2x. 3 minus 6 is -3, and that's it. That's g of f of x. And with all rational expressions, we want to state the restrictions. So we say x is not equal to, it should be, what, -3 and +1. I think if you factor that down, the values that make the denominator 0. So x plus 3, x minus 1. So yeah, that's going to be it. So x cannot equal -3 and +1 because that would give us 0 for our denominator. Well, what about the evaluating? Well, evaluating is pretty straightforward. G of f of x is this function, so g of f of -2, I can just plug -2 in. So -2 squared plus 2 times -2 minus 3, and you get 4 minus 4 is 0, minus 3, so it's equal to -1/3. Pretty straightforward. Figure out what g of f of x is, then plug -2 in for the x's, like we've always done our evaluations. Real quick, let's identify the domain of this function. So if I looked at my original input function first, f of x has a domain of all real numbers because it's a polynomial. Remember, all whole number exponents we don't have any restrictions on. So -infinity to +infinity. Let's try to make it look a little bit more like infinity. Now the domain of the final function, g of f of x, we can see that it had these restrictions on it. So it would be -infinity up to -3, skip over it, -3 up to +1, skip over it, and +1 up to +infinity. So that's the final expression's domain, and since the original domain, or the input function's domain, was -infinity to +infinity, there's no extra restrictions to put in there. So this ends up being the final domain of our function. So remember, when you're doing domain, look at your input function, which in this case was the f. Look at your final function, which is this rational function we had here, and then you combine the restrictions from both, the domain restrictions from both, to create your overall domain. Now, as I was saying, there's another way we could look at the evaluation stuff, and it's instead of doing all this work, because sometimes they don't ask us to find the g of f(x). Sometimes they just say evaluate. So if they're doing that, I don't have to find all this. Just think of what we're doing. I'm taking my f equation, plugging it into my g equation. Well, if I want to do g of f of -2, that is just g of f of -2. So what's to stop me from figuring out f of -2? So taking -2, plugging it into f, and then taking that answer and plugging it into g. So what we get is this expression. I'm going to clear myself some room here so we can write it next to the other one. If I did f of -2, f of -2 is going to be -2 squared plus 2 times -2 plus 3. So 4 minus 4 is equal to 3. Then g of 3, we're going to take that answer, plug it into the g equation. 1 over 3 minus 6 is -1/3. So if I don't want to go through the hassle of finding the g of f of x and then evaluating, I can just use this idea of evaluate for the input function and then take that value and plug it into my output function, my g function. So if we looked at number 2 and we evaluated that way, if I said f of g of -2 was f of g of -2, and I took -2, plugged it into g, and then that answer into f, I can just do my g equation. G of -2 is square root of 4 minus x, so 4 minus -2. So that's going to be equal to 4 plus 2, which is square root of 6. Take that answer, plug it into the f equation, -2 into g, g into f. So 3 over square root of 6 squared minus 2 gives us 3 over 6 minus 2, which is 3/4. So it's a little bit quicker than doing all the find your composition and then evaluate after that. You can kind of just take it in pieces however you want to go. So 2 techniques there to evaluate. But it's the same idea of what evaluating and composing is, using one function to define the other function. The input for one then becomes the output for one then becomes the input for the other. Now let's go through and do the actual composition on this one. So f of g of x, I'm going to take my f of function, my output function, and it's 3 over, not x squared, but something squared minus 2. Give myself some room so y'all can see this. So 3 over something squared minus 2. That's the f equation. 3 over something squared minus 2. Then I'm going to plug g into that. So start with f, and then we're going to plug g into it. So that's just the square root of 4 minus x. Well, as we go through, remember square root squared is just going to give us the radicand minus 2, and 4 minus 2 is going to be 2. So we get f of g of x is equal to 3 over just 2 minus x. So that's those two functions composed. Now, to do domain, again, give myself some room to work. If I wanted to do domain, I go to the original function, the input function. That's the g function. So the domain of g of x is going to be where the radicand is greater than or equal to 0. 4 minus x is greater than or equal to 0. So add your x over, you get 4 is greater than or equal to x. Or we can say x is less than or equal to 4. Now, domain of the final function, if we look at it, it's a rational function. So rational functions, you say denominator is not equal to 0. Correct? Can't divide by 0. So add your 2 over, so 2 cannot be x. So when we put all of this together to make one big function, we have to have only the numbers less than 4 and excluding 2. So it's going to be negative infinity. So the domain of f of g of x is going to be from negative infinity up to 2, but excluding it. All right, that's how we write exclude 2, and then from 2 up to 4. And we can equal 4 because it's or equal to. So this ends up being our final domain. Take the domain of the input, domain of the final function, and then we combine all that information together and write it as one master domain there. So that's composition functions, evaluating, finding domains, actually creating them. I want to talk one more thing about decomposing functions. That's kind of taking a function and see where we can break it up into what was composed to create it. So give me a second, I'll get that information up for you. All right, last thing I want to talk about, decomposing functions. That's where we take one function and try to break it up into two functions that we say were combined by with composition. We write one function as a composition of two functions. Right now, if you want to pause the video and try to do these two on your own as far as coming up with two functions that were combined, f and g of x, to create each one of these, go ahead and do that. I'm just going to go right into it and show you how I think about these when I'm decomposing. But it's up to you whether or not you want to try these on your own first. So when I am decomposing, when I'm trying to break functions up, it's really just pick one thing to define in terms of the other. But you have to find something that occurs multiple times, or sorry, the same thing that occurs the same way in every place in the function, or it's just one expression that's chunked together. So as we can see right here, see how we have the x minus 2 that's chunked together? We don't have x minus 2's anywhere else or any x's anywhere else. So we can say this x minus 2 could have been inserted, could have been inputted into the function. Well, if it had been inputted, what would we be left with? Well, if we take the x minus 2 out, we'd have been left with 4 over something cubed. We just take the x minus 2 out, and the rest of the function that's left should be our f of x function. So if it's f of x, we define it with an x. So 4 over x cubed is my f function. And that's only because we're saying g was our input. If we could have flipped how we define these if they just said g of x. So they said g is the input, so it looks like x minus 2 has been inputted, and that leaves me 4 over something cubed, so that something just becomes an x because we're defining everything in terms of x. So if we look at number 2 here, what's chunked together? Well, I don't want to just take x, that's, because that's just x. Yeah, technically I could say g of x equals x, and then it was plugged in there for x, but that's boring. We're not going to do that. Let's get a little more creative. What's a chunk here? Well, I see this whole x plus 3 as a chunk. So if we take the x plus 3 out, what's left should be my f function, my output function, which is square root of something. So we take the whole x plus 3 out, we get square root of something, and that something happens to always be x, because that's what we are defining it. So if we were to think about putting this back together, g going into f, x plus 3 would replace that x, and you get square root of x plus 3. Now you can get a lot more creative. I mean, I could have made this x plus 4 and then made this x minus 1. You know, again, you can get creative on how you define these. But that's what we mean when we're talking about decomposing functions. Identifying one function as two other functions put together. And why that's very important, that skill to be able to do, is because this right here has a particular set of traits to it, this 4 over x cubed. The square root of x has a particular set of traits to it, and then we see this other function as a manipulation on that. Kind of like we do with parent functions and transformations of parent functions. So, very important skill to be able to be able to decompose and break functions into different types of smaller functions that we can then focus on the individual characteristics of. So that's it for combining functions. Again, mostly about notation there at the beginning, so make sure we're good on the notation. And then composing functions is just evaluating at an equation instead of a specific number. That's it for this, and I will see you in class tomorrow, guys.